You're familiar enough with this setup, or one similar to it, from your home experiment work back in Unit 2. I'm plotting the frequency response of this amplifier, in fact. Well, you know from experience that measurements like these turn out to be a very repetitive sequence of operations. Just the sort of job suited to microelectronics, in fact. So if microelectronics is good at the job, what am I doing here? Well, this thing is a microcomputer, and it's meant to be controlling the measurements. But as it stands, it can't handle the pen and paper directly. So let's give it a graph plotter and a printer. Of course, the computer won't be able to manipulate the generator scope. It was designed for humans only. But instruments like the plotter and the printer are designed to be remotely controlled by other instruments like the computer. And that's what these cables are for. So if we wanted this setup for real, we'd have to replace the generator scope with a remotely controllable signal generator. But things aren't quite this simple, because we're going to run into interface problems. Look over here. Here's the computer, and these are the test instruments. And between each one and the computer is an interface. So we end up with what's known as a star structure. Now, the chances are that each instrument will be manufactured by a different company, and so each interface would have to be a special. The voltage levels, the coding, timing would all be different, and probably even the connectors. If I wanted to add another instrument or replace, say, the DVM with another model, I would have to redesign the interface. If I wanted to change the computer, I would have to redesign 4 interfaces. So with this sort of system, where we have no standardization between manufacturers, the arrangement becomes very inflexible and expensive. But suppose that all the manufacturers built their instruments, including the computer, to work and generate off a standard set of control signals. I think you can see how that would simplify things considerably. But is this standardization just a pipe dream? Here's David Dack of Hewlett-Packard.
Well, it's not such a pipe dream as you might think. Since 1975, a standard has existed, and it allows a system like this to be rigged up with no hardware design effort. It's doing the same job as Nick's system, plotting the frequency response of this amplifier. I've got a desktop computer controlling the operation and performing the calculations. There's a signal generator, a DVM, a printer, and a graph plotter. And if I press the run button, off it goes. You've seen this done automatically before, but the great thing here is that all these instruments are off the shelf with no special interfaces. So it's a simple job to unhook, say, the DVM and plug it into another totally different system tomorrow. As long as we work within this standard, there are no messy interface problems to worry about, and we have a completely flexible system. Another feature you'll notice is that each instrument isn't connected by a separate cable to the computer, as with Nick's star system. There is just one cable run linking them all together. So this gives a parallel bus structure, which diagrammatically looks like this. Well, this standard is known in America as the IEEE 488 standard, and in Europe as the IEC 625. We've just called it a general purpose interface bus, or the bus, and it's being rapidly adopted by most instrument manufacturers. We'll be spending the rest of this program looking at a few aspects of it.
Well, now we've got an idea of what the general purpose interface bus is about, I'd like to get away from thinking of just one particular system and think more in terms of a general system. That's shown here, where we've got 4 devices, A, to D, connected in parallel form on a bus structure. These devices could be anything. It makes no difference, as long as they adhere to the standard. Now, this bus structure imposes certain constraints. One of them is that we must use open collector drivers. Let me show you what I mean. This is an open collector bus driver with its internal circuit. We've just got a single transistor with its collector connected directly to the output. For the circuit to work, this collector needs to be tied externally to plus 5 volts through this pull-up resistor. The idea is that when the circuit wants the output to be low, it switches this transistor on, which puts the output at about 0.2, 0.4 volts. When the output needs to be high, the transistor switches off, and the output is then pulled up to the high level by the resistor. All right, but what we want to know is what happens when two of these outputs are connected together. I've only shown the output transistors here just to keep things simple. Device A and device B connected to the same line. And here's the pull-up resistor. When this light's on, this means that the line is high. Right, let's start with both these transistors in the on state. i.e., they're both trying to pull the line low. The lamp isn't shining, so the line must be low. Now, suppose that transistor A was switched off. If it were on its own, that would allow the pull-up resistor to pull this line high. But B is still on. So what do you think will happen when I switch A off? Right, the line stays low because B is still holding it down. I have to switch B off as well before the line goes high. Let's look at the timing diagram. With A and B both on, the output line's held low. If I switch A off, that tries to release the line to go high, and that's what the dotted line shows. But because B's still on, it holds the line low. It's only when A and B go off that the line finally goes high. Well, that's the open collector driver. I've only shown it here for 2 transistors, but the process generalizes for any number of outputs. That is, they all have to be off before the line can go high. Before I finish talking about outputs, there's another property of the bus structure that I must cover. So let's go back. Well, this property is called bidirectionality. It means that information can pass in either direction along the bus. This is a feature of most bus structures, and it implies that both the input and the output from a particular device share the same set of wires. This may be a little surprising to you at first sight, because up until now, you've been used to separate input and output lines. In the bidirectional case, they're connected together like this. Notice that we have open collector outputs, and that enables us to connect them straight together. In fact, this whole bus structure uses open collector devices. What happens is that B's output passes this way to C through this inverter, and C's output passes this way to B. So we have two-way flow. Notice that the output connects directly to the input, but that's no problem because we can always ignore it if we want to. Well, that's open collectors and bidirectionality covered. So how do these ideas apply to the general purpose interface bus?
The first point to make is that the general purpose interface bus is an asynchronous bus. But what do we mean by an asynchronous bus? In this system, we have these various instruments all connected to the bus, and information and data flows between them. For instance, the computer might pass information into the DVM, telling it what range to switch to. But because the computer doesn't know how long it takes for the DVM to switch ranges, it has to wait to be told when it has happened. This is the essence of an asynchronous operation. Each instrument takes its own time to do things, and each one needs to be able to say when it's ready or not ready, as the case may be. In all this toing and froing of information between devices, there's a certain analogy with human interaction, and in fact the vocabulary draws upon it. For instance, a device when it's putting information onto the bus is called a talker, and a device when it's taking information from the bus is called a listener. What we need now is a communications protocol for the talkers and the listeners, which lets one know when the other is ready. This is called handshaking, and it's handshaking that I want to look at now. Let's think about the case where we have a talker and just one listener. Information flows from the talker to the listener along the data bus. But it's no use the talker talking until it knows that the listener is listening. So the listener needs to be able to tell the talker when it's ready. So there's a separate wire running from the listener to the talker. Let's call it ready for data. So when this wire goes high, say, that tells the talker that the listener is ready to listen. The talker can then put data onto the bus. And it pulls down on a second line to say that the data is valid. Once it receives the data valid signal, the listener then reads the data, and once it's got it, it can signal the fact to the talker by pulling ready for data low again. The talker can then remove its data and let its data valid line go high. That is one complete handshake cycle. And because only 2 extra connections are used in addition to the data bus, it's called the 2-wire handshake. Let's see it again, this time with a timing diagram. The listener is ready, so it lets ready for data go high. The talker then puts the data on the bus and pulls data valid low. The listener reads the data, and once it's got it, it pulls the ready for data low again. The talker recognizes this and removes the data and lets data valid go high, and we're back where we started. And so the process continues. Well, that's the case with just one listener. But in general, we'll have more than one listener on a bus. Here, for example, where the DVM might be talking, both the plotter and the printer will be listening. Well, we want to see how the 2-wire handshake fares there. But before we do, prepare yourself, like in all good stories, for a twist. For consistency, the standard insists that all signals should be ground true. That is, low for true and high for false. All this means is that the ready for data line has to be called not ready for data. It still goes high and low in exactly the same way as before, and it still means that the listener is ready when the line is high and not ready when the line is low. So with that in mind, let's see how the 2-wire handshake fares with 2 listeners. The 2 listeners are B and C. And notice the line is now marked not ready for data. When neither B nor C are ready for data, not ready for data is true, that is low. Suppose B becomes ready for data, but C doesn't. B will try to let the not ready for data line go high. But because of the open collector outputs, it will be held firmly low by C. It's only when both B and C are ready that not ready for data can go high. Now the talker knows that both listeners are ready, and it issues data in the normal way and tells both of them that data is present by pulling data valid low. Well, that's fine so far, and you can see why we wanted to signal ready for data by a line going high. It allows the talker to hang on until all the listeners are ready. But what happens if B finishes with the data before C has had a chance to read it? Because of the open collectors, B on its own pulls the not ready for data low. And on the 2-wire handshake convention, that tells the talker to remove the data, which unfortunately C still hasn't read. Well, that's no good. So we have to add yet another wire called not data accepted. A device holds this line low until it has accepted the data. Then it tries to let it go high. And now the talker doesn't remove the data until the line does go high. Well, B will try to let not data accepted go high to say that it has accepted the data. But the line won't go high until both B and C have accepted. There. Now the talker positively knows that B and C have both read the data, and it can safely remove it from the bus. Let's see it through again. B's ready, but C isn't. Now they're both ready. Not ready for data goes high, and the talker issues the data. B's finished with the data, but C still hasn't. Now C's also finished. Not data accepted goes high, and the talker withdraws the data, and so the process goes on. It's called the three-wire handshake.
So we can see here that as well as the data bus, shown in red, we have the three handshake wires. Now, like any controlled conversation between a collection of people, things go smoothly only when there's a chairman or controller in charge. It's the same with the bus system. Devices have to be told when to talk, when to be quiet, and when to listen. In David's example, it was the computer that fulfilled this function by controlling the other instruments. Normally, the controller can control, talk, and listen. But how does it tell a device which can talk and listen, like the DVM, when to do what? Let's return to our diagram, which now shows the controller, talkers, and listeners. Well, each device is given a talk address, if it can talk, or a listen address, if it can listen. So if the controller wanted this device to talk, it would put its talk address on the data bus. Now, in order to distinguish this address from real data, which also appears on this bus, there's an additional line running between them. This is called attention. Well, you'll understand that better if you see how it works in practice.
I've got a demonstration set out here. This is a bus analyzer, and throughout these demonstrations it will always be the controller. It lets me control all the bus functions with these data and control switches. The state of the data lines is shown on these LEDs, both in octal and as ASCII symbols. Here you can see the state of the three handshake lines: data valid, not ready for data, and not data accepted. When the LED is lit, the line is pulled low. This LED shows the state of the attention line, which Nick has just been talking about. To start with, let's just send some characters to the printer, which has a listen address of 44 octal. I set attention true because I want to send an address. I put 44 on the data lines and execute a handshake. That's addressed the printer to listen. Now, suppose I want to print the characters A, B, and C. First, I put A on the data lines, set attention false because now I'm sending data, and handshake it. A is now stored in the printer. Now for B, handshake, and C, handshake again. These characters are now stored inside the printer, and to print them, I send a line feed, which is octal 12. I'll send a few more to step the paper so that we can see it. Let's try something more ambitious. Here's that DVM again, and I'm going to program it to measure the value of this resistor and print the result on the printer. This DVM is good for this demonstration because you can see what range it's on by these LEDs in the push buttons. First, I set octal 77 with attention true. This is the onListen command, which will tell all devices to stop listening. The DVM's listen address is 43 octal. So I'll send this with attention true. Now you can see the DVM indicating that it's listening. Now, with attention false, that means I'm sending data to the DVM now. I'm going to send F4, which selects the resistance range. So I send an F, and then a 4. And if you look at the resistance range button, you should see the light come on now. With attention true again, I can tell the DVM to talk by sending its talk address. That's 103. So if we look at the talk light, when I send the handshake signal, now the DVM is addressed to talk. Right, the printer's address is 44. So if I send that address, that's told it to listen. The devices are addressed now. The printer on the bottom as a listener, and the DVM on the top as a talker. So if I put attention false, the DVM talks out its answer. There, that resistor is 2.52 kiloohms.
Well, that's about as far as we want to go with this interface. But for completeness, I ought to mention that there are another 4 wires included in the bus. These 4. They can be used for more sophisticated functions, and they are briefly mentioned at the end of units 15 and 16. Now, you'll read in the unit that this system is limited to a maximum cable run of 20 meters, and under certain circumstances can be very limiting. But it is possible to buy a device like this, which, through an intermediate post office modem, can connect my bus system here to one, say, in California. The device, it's called a bus extender, converts the parallel data on the bus into serial form, suitable for transmission over the public switch telephone network. At the other end, a similar device converts it all back into parallel data again. Now, telephone lines limit the data transmission rate, and if we want to go faster, we can use a different type of bus extender. One like this, which will work with up to 1,000 meters of optical fiber. If we follow it along, we should find David at the other end.
Well, the output of my bus extender is connected into the back of this plotter.
And mine to the computer. And if I press the right button, it should communicate to David's plotter over the fiber link.